Okay, good day. This is Math 130 Intro to Statistics. I'm Professor McCulley, and this is the last lesson, number 27, linear regression. Let's get to it. All right, so the learning goals for today, we're going to find the equation of a regression line, and we're going to predict some y values using the regression equation. So what is that exactly? Well, in the last section, we talked about correlation. And in this lesson, we're going to take that correlation and further refine it into a linear equation that best approximates the set of data that we were given. And the way that they do that is through the regression line. And so, as a definition, the regression line, also called a line of best fit, is the line for which the sum of the squares of the residuals is a minimum. And so there's this word residual that I'd like to talk about. The definition: a residual is the difference di between the difference or between the observed y value and the predicted y value for any given x value. So this is a very, very simplistic vision of what we're going to do with a regression line. But here we see four pieces of data, and we could say, using just the eye test, that they kind of correlated. As we go left to right, they tend to go up. And so a line of best fit, what the calculation we're going to do is they're going to take these distances right here, and they're in green, and each one is different. And what they're trying to do is what they're going to try and do is they're going to try and take this and make this line so that the sum of the squares of all of the distance of these green lines is as small as it can possibly be. And when it's as small as it can possibly be, then we have our line of best fit. Now, we're not going to try and prove that calculation because it involves calculus, but we do know what those equations are. All right, so the equation of the regression line, the equation of a regression line for an independent variable x and a dependent variable y is y hat, and so this is going to imply a regression line, equals mx plus b, where y hat is the predicted y value for the given x value, and the slope m and the y-intercept are given by these two equations. And so the equation that you would have, and again, we're not going to do this by hand because it's a pain in the butt, is you would go through and to calculate this one, you would multiply x, all the x times y, and add them up, and then multiply by the number of elements, the number of data sets that you had. In this case, for this one, there would be 4. Clearly, that's small, but the more pieces of data, the more elements you'd have to multiply. Then from that, you would subtract. Well, the first thing, this implies that you add up all of the x values, and this implies you add up all of the y values, and then you would multiply them. So you do the sum of the products, and then the product of the sums is the way that you would say that. And then once you've made that calculation, you'd come down here, and you take all of the, you square all the x values, and add them up and then multiply by the number of x values. And then from that, you subtract the sum of all of the x's, and once you've added them all together, then you would square it. And so then you make that calculation. That would be the slope. And then the y-intercept is literally the average of the y's minus the slope that you calculated from over here times the average of the x's, and that's what this implies here. The average is the sum of all of the values divided by the number of values that you have, and so that's what this expression implies. All right, note the regression line will always pass, and there should be 2 s's there, so let's put an s there and hit save. Will always pass through the point x bar y bar. And so what we mean by that is that this will always, the regression line will always pass through the average of the x values, comma, the average of the y values. All right. Application of the regression line. When correlation between x and y is significant, we checked that on the last lesson, the equation for the regression line can be used to predict y values for certain x values. Prediction values are only meaningful for x values close to the range of the ordered x values. And again, when we say close, that's kind of a vague term, and that's really going to depend on the situation. When the correlation between x and y is not significant, then the best predicted y value is always going to be the mean of the y values. So let's take a look at what the steps that we're going to do, and these should look very similar to the last lesson because we found the correlation coefficient by this method, and we kind of skipped over the actual regression part. And so since that's already been in there, I'm just going to really quickly review the list, and you can, use this when you're doing the practice work. But you're going to, again, anytime we use the stat, you're going to hit the clear list. So remember stat, clear list, and then L1 and L2. And then we're going to enter our data. And remember, since we're entering bivariate data, you got to make sure that the X's all go in the L1, and then the correct corresponding Y values go in the L2. Then we're going to open a window to fit the data. And remember, you don't want to put your data right on the edges, so always make your window a little bit bigger than your data. And then you can graph the scatter plot if you want to look at it. You can find the line of best fit by going stat, calculate linear regression ax plus b, and again, that's what we did to find the correlation coefficient. And then make sure we hit L1 and L2, and also make sure that your frequency list is clear for that. You don't want to have that. And then we can graph the equation. And then if we need to make a prediction, which is what this lesson is about, we'll hit second and then trace in value, and we can plug it in. And if it's multiple values, you could also use a table, but you'll see what that looks like here in a moment. All right, so my example for today, the number of hours 11 students spent studying for their Math 130 final exam and their final test scores are given below. And so we see that. And so my first question is, at the 0.01 level, does this show significant linear correlation? And then 2, what is the equation of the regression line? 3, evaluate the regression line for x equals 8 and interpret the results in the context of the problem. And do you think that the equation will adequately be predictive for x values in the 30 to 40 hour range? What makes you come to this conclusion? All right, so lots of stuff going on there. Let's talk about this data set here. And so essentially what we're reading is the person that spent 40 hours, they got a 40% on the final exam. Person who took 2 hours, they took 51, got a 51%, and then the person over here who spent 12 hours, 91%. And that's just Professor McCulley's hint that you might want to do some studying for this final exam that's coming up here very shortly. Okay, so the first thing that we're going to do is we're going to go to our graphing calculator, and we're going to enter this data. And when I do that, I'm going to hit the stat. And we want to, since we're entering new data, we want to clear out the list. So 4, second, and then 1 for L1, comma, second, 2 for L2. We'll hit done. And then we're going to enter our data here. So we got to hit stat, and then 1 for edit. And then in this first column, we're going to put the x value. So the data was presented horizontally. We're going to enter it vertically. And I have it on a piece of paper here. So 0, 2, 4, and then there are 3 5s, and then there are 2 6s, and then there are 2 7s, and then there's a 12, and then I hit the right arrow key to get into L2, and so 0 got a 40, and then there's a 51, and then a 64, and then a let's see here, it's a 73 for that first 5, and there's a 70, and then a 73, and then There's, wait a second. I screwed that up. Let's go back up here. The first 5 has a 68, and then there's a 73, and then a 70, and then another 73 for the first 6. Let's make sure I get this right here. 77 for the second 6, then an 80 for the first 7, and then a 77 for the second 7, and then a 91 for the 12. That looks good. All right, so if I wanted to take a look at the scatter plot for this data, I can hit the window button, and our x minimum -2 works. The highest value was 12, so we'll go max of 15, y scale 1, or x scale 1, y minimum. We want to see the x-axis, so I put -5 there. And since this is a test with a high score of 100%, I put my y max as 110, and we'll go by tens, and that should work. And then I want to turn on my stat plot. So one of the ways that we can turn it on is if we hit the y equals, we'll clear out that stuff, and I have it turned on. You come up to the stat plot here and highlight plot 1, that'll work. And if I hit graph and everything turned out right, we see that this data, yeah, it kind of looks linear, and clearly there's a little bit of positive correlation in there. And so we want to verify that, and we do that the same way we did for the last lesson. We're going to hit stat, we're going to go over to calculate, and we're going to do the linear regression for. We want to make sure that X list is in L1, our Y list is in L2, our frequency list is empty, and then here's this store regression equation, which is nice for the TI-84s. Well, we can actually tell it to plug it into the calculator if we want to use it. And the way that we do that is you hit the vars button, you go over to Y vars and function and hit 1. And if you don't do that, it's okay. You just have to write it down. But this one will do it for us, and that saves us a little bit of time. And so I'm going to hit calculate. And so here we have all of the information, and it gives us the equation that we would use. So y equals ax plus b. I know that we said it was m, but the calculator says it's a, so we're just going to kind of use our imaginations and say that that's the slope. The slope 4.38, well, it would be, I round this one up, that may round that one up, so it would be 4.3890, and then 45.913, I would round that one, so 6, and then the r squared value, and then our linear correlation is 0.9549. So let's start trying to answer some of the questions. At the 0.01 level, does this data show significant linear correlation? So the first thing I want to do is I'm going to look at my table here, and so we have 11 items, and at alpha equals 0.01, we need a 0.735. All right, 0.735. So at the alpha equals 0.01 significance level, our R equal to 0.9, what was it, 54, we'll just go 50, 5450 is greater than the required 0.7, I already forgot it, 0.735 for 11 items. Thus, there is evidence for linear correlation. Number 2, Number 2 asks, what is the equation of the regression line? Well, the equation of the regression line is just y equals mx plus b using these values. So we can say y equals 4.389x plus 45.914. And then for number 3, it says evaluate the regression line for x equals 9 and interpret the results in the context of the problem. All right, so if we want to evaluate y equal, we'll have to use our y equals. And remember, we said store the regression line, and so it stored it out to all these decimal places. And we could bop over and we could see all of the values that we needed to see. And if I hit graph, we can see that that's a fairly good regression line. These data points look kind of far away, and so there's a lot of points here, and since they're above and they're only above by a little, if we're minimizing the least squares line, these have a bigger impact than these little ones here. Anyway, if I wanted to take a look at, and I'm going to do it 2 ways. If I wanted to evaluate x equals 8, I can go second, and then I can go trace, and I can hit 1 for value, and we can plug in 8, and we would get 81.0203. So when x equals 8, the predicted y is equal to 81.03. And they want us to interpret the results in the context of the problem. So my conclusion is, if a given student were to study for 8 hours, it would be reasonable to expect the student to earn an 81 on the final. All right, now again, is that going to be perfect? Every student that does 8 hours is going to get an 81? No, but according to our prediction, we should be fairly close. So number 4 says, do you think that this equation will adequately be predictive of values of x in the 30 to 40 hour range? What makes you come to this conclusion? All right, well, our graph doesn't go up to 30 and 40 hours, but what we could do is we could make a table and take a look at that if we wanted to, and that's fairly easy. So I'm going to go second, and I'm going to table setup. Second window gives me the table set, and I'm going to turn this, make sure that this is to the ask. And if I go second table and I enter 30 and 40, I get a 177 and a 221. And so if this is a percentage-based test, clearly these two do not make sense in the context of the problem, because you can't earn 177 on a test that the best you can do is 100%. And if you can't do it for 30, you can't do it for 40. So this THIS regression line is not adequate. ADEQ for study times between 30, and let's do a better job, 30 and 40 hours, because the prediction for those times is way above 100%. All right, that's all I got. So the final fun fact of the day, Stan Lee loved doing the cameos in the MCU movies so much that he actually wanted to expand the role and supposedly asked to be considered to play the role of Odin in the first Thor movie, and that role eventually went to Sir Anthony Hopkins. But we would have been much better off seeing Stan Lee more often. That's all I got. Have a good day, folks. Bye.